Good afternoon, folks. I would like to welcome Dr. Rajeev Shorey, who is the CEO of partnership between the University of Queensland in Australia and Indian Institute of Technology, or IIT Delhi. It's called the Queensland IIT Delhi Academy of Research, and is an adjunct faculty in computer science and engineering in IIT Delhi. IITs are among the premier educational institutions in engineering and technology in India, and certainly the Far East, Southeast, and South Asia and Far East, and worldwide in some ways too. So, Dr. Shorey received his BE degree in computer science from Indian Institute of Science, Bangalore, and his MS and PhD in electrical communication engineering from the same place. Over his career, he has done several things. He has been with TCS, which is one of the Tata Consultancy Services. It's a research and innovation labs, General Motors India Science Lab, IBM India Research Lab, and Sasken Technologies. He served as the first president of the National Institute of Information Technology University from 2009 to 2013 before joining the Tata Consultancy Research Labs. He has published more than 70 papers in a number of international conferences and journals, and has been issued 12 US patents. His broad area, he's going to discuss some aspects of recent investigations in the intersection of ML, and that's machine learning and edge computing. He's a fellow of the Indian National Academy of Engineering. He was elected in 2007 to that, and ACM has recognized him as a distinguished scientist. This was in 2014. And he's a fellow of the Institution of Electronics and Telecommunication Engineers, India, and a senior member of the IEEE.
Thank you very much, Professor Ram. I can walk around, right?
Yes.
Okay, great. I like to do that because I do take a lot of classes. So thank you very much, Professor Ram, for the very kind introduction. It's a great pleasure to be in LSU, back after 3 years. I was here in 2019, just before the shutdown in 20, and I've been here many times. So this is, I think, my 4th trip to LSU. It's always a pleasure to come here and to interact with faculty members, with students. It's a great pleasure to see LSU students here too. So what I will do today is to talk about some very important, interesting areas. I think it's one of the things that we keep grappling is what are the areas that are not only hot, but that are also very impactful. The industry loves it, academia loves it. Fortunately, it's turning out that edge computing is now becoming, as you all probably know very well, becoming a very important space. And at the edge, the whole machine learning, the AI, machine learning, and deep learning, how do they, what's the marriage of AI, ML, and DL, deep learning on edge, is becoming very important, right? So let me go take you through, change this. Change this, this doesn't work. Change the slide real quick. I don't see. No, no. Perfect. Thank you so much. All right. Thank you so much. So here is my agenda of the talk today. I'm going to start with the introduction and motivation, and I think it's important to start with what we mean by edge intelligent systems. There's a lot of work going on in edge, as all of you may know very well. But what are edge intelligent systems, right? And where are we heading to? So one of the things that I always do in the talks that I give, not only in my courses, but even outside, all over, is to figure out what are the open research challenges, to understand and to highlight what are the open research challenges, because I think that's those set of areas or challenges are something which are going to excite the students much more than our actual results, because that's really in past. So we look at the edge intelligence systems, and then it'll turn out that paradigms such as federated learning, and there are other paradigms which I unfortunately cannot talk today because of the time paucity, but there are something like multi-agent reinforcement learning. MARL is becoming a very important area of work. Federated learning, distributed federated learning is becoming very important. And we'll have an opportunity to look at some interesting work interesting results coming out from IIT Delhi from my students. The part one of my talk will talk about the federated learning at the edge nodes. We'll have some very interesting performance results. If you go back in time, there's a lot of work in talking about federated learning on the edge, but we've seldom seen some interesting results, not just the simulation results, but I think the prototype. And one of the lessons we've learned is that it's good to work on Python. Everybody works on Python or PySift and so PyTorch and so on and so forth. But you can really implement the algorithms even on a very simple environment like your Raspberry Pi or Arduino boards or anything equivalent to RPi. Then you really have a very strong contribution, because you really it's a POC which can be extended to more complicated devices. So the lesson, I'll share with you the lesson that we have learned. And then what I will do is in the second half of the talk, so it turned out that a lot of people are talking about running CNNs at the edge, and I will do that too in this talk. But how do you run CNNs or the deep neural network efficiently on an edge? Because as we all know, edge computing is edge is a resource constrained environment, right? All of us know the edge is not the cloud. Edge is between the IoT and the cloud, right? So it's by definition a resource constrained environment. How do you efficiently run CNNs on a resource constrained environment such as edge devices? Some interesting results over there which came out in the last 6 months to 1 year. And I think the most important part, the last 5-10 minutes, will be what are the future research directions that are going to keep us busy for a long time to come, okay? So that's the overview of my talk. I think it's important to acknowledge my students. I really have been very, very fortunate to have some great students. Manupriya Gupta is now in Carnegie Mellon, so she just joined CMU, I think, a few weeks ago. She's starting her, graduate courses over there. Pavas Goel is one of the stars. I call him a water walker. He's joined a company in Delhi called Graviton, which I think they do financial analysis and all these stock trading and so on and so forth. Pavas is one of the top 60 in India in the IIT JEE exams. All of you know JEE. So he's one of the water walkers, and I'm glad that Pavas was my student. Of great work. I coaxed him to come to US for a PhD, but I think a lot of students that go for jobs than PhDs now, unfortunate. I have two very good students who are working with me now, Saurabh Bansal, Manav Bansal. They're in the final year BTech in IIT Delhi in the CS department. We're still investigating some interesting stuff in federated learning, and I'll talk a little bit about that towards the end of my talk. I also work with other universities like the Delhi Technological University, which is really a very, very upcoming, a very established university. Tanmay, Avnish, Ishan, Anirudh have done some wonderful work in CNN on the edge. I collaborate with Rohit Verma, who's now in Intel Research Bangalore. He was a postdoc in Cambridge University and did his PhD from IIT Kharagpur. And of course, Professor Saran is my collaborator from the CS department at IIT Delhi. So a lot of collaboration. One of the lessons I've learned is if you don't collaborate today, no matter how good you are, you really cannot go beyond the point. You're limited by your own understanding, no matter how good you are, but you won't get ideas from other folks in the group. So it's very important to have global collaboration. So that's something I'm absolutely gung-ho about ever since I started my career 20 plus years ago, 25 years ago. Let me start, let me go straight to the point. So we all know 5G, right? Many of us have worked in 5G. In fact, Gaurav, you are very active in 5G in Cisco, and Supratik, all of you know that. And we know that 5G defines 3 broad categories, right? All of us know that. Enhanced mobile broadband, mission critical services, massive IoT, right? So these broad cases have their own metrics, they have their own parameters, right? There is no one parameter that defines all 3 categories. So we all know that, right? But we also know that if you look at 5G, and if you study the 5G standard, the 5G, the various technical standards and the literature, it turns out that the edge is a very important component of 5G, right? We will come to what the edge is and why we need the edge, but the edge nodes are playing a very important role. 5G defines edge very clearly. It doesn't go to details because the details are left to the implementation or to its proprietary, best left to the organization implementing it, right? But the edge sits somewhere at a very high level. The edge nodes sit between the IoT devices, I call them the last mile, and of course, so they sit between the IoT and the cloud or the servers over here. Now I'm going to use the word cloud and the servers and the data centers interchangeably because they really want the same thing. So servers and cloud is interchangeable. There's not much difference. So now, why do we need these edge nodes? We need the edge nodes primarily because if you don't have the edge nodes, so you know one of the interesting things we learn is always ask questions through counterexamples, right? If you don't have the edge nodes, then whatever you do at the IoT will go to the cloud, right? It will be processed in the cloud and you'll get the results back on whatever protocol. Doesn't matter what the protocol is. But the latencies are very high. And you may say, well, it doesn't matter. I don't care about latency. Well, but I do care because some applications like autonomous driving, right, cannot afford such high latencies. You know, you have to have very tight upper bounds on latencies. So when you want that, you know, whether it's healthcare or whether it's autonomous driving or many other apps that we were talking about, so the other day, you really need these edge nodes. But when you have these edge nodes, it turns out that these are not the cloud, they're not the servers. They're also cheaper, so the resources are not as pronounced or as much as cloud. So you'll have limited processing power, limited memory, and you have to do a lot of processing on these edge nodes. That's the focus now. I remember way back in time when I was in General Motors research, the whole idea was, and that's when the V2V communication had started. We were supposed to run the very complicated algorithms, for example, the elliptic curve cryptography at the edge node, right, which is the compute platform in the vehicle. So it started really way back, but now it's become a very important area. So let's now go straight to the point. What is federated learning and what's new about the area and why is this area a very important area? Why is it attracting so much interest, right? So let's look at federated learning and I'll come to what a faulty edge ecosystem is, okay? So let me give you a very quick overview for those who may not know about federated learning. Now, a lot of our colleagues, in fact, I have this friend at MIT, Sachidanandan, who works who's a postdoc at MIT. He said, Rajeev, federated learning is nothing new, it's just distributed systems. And the answer is yes, that is true. Federated learning is nothing but old wine in a new bottle. It's a distributed system. But the difference is that this distributed system is running machine learning algorithms in a distributed manner. So let's take an example, right? So here's your central server. You still have a central server. So remember, that's an assumption, and I'll relax it later on. You have a central server. Let's say you have k nodes over there, right? 1, 2, 3 k nodes over there. So the k nodes are also called the worker nodes. I'm going to use the word worker nodes because they are the ones that work on the data. What you do is that you don't, so one of the key mantras of federated learning is privacy preserving. It's a privacy preserving paradigm. You have to preserve the privacy, which means you cannot I will not send my data to the server and then allow machine learning to extract some nice inferences. I'm not going to do that. I don't want the data to leave my device, right? So the data will always be at the worker nodes. The worker nodes are the nodes where the distributed node, the leaf node, if you will, right? What I'll do is I'll instead send the model to the worker nodes. Listen to this carefully. The machine learning model, whatever be the model, doesn't matter what the model is. It could be any model. We'll come to what the models are later on. And the model will then do its job. It will train over here, do a local training. It'll send the metadata back. The metadata really is the model back to the central server. And everybody is going to do the same, right? So there are k nodes. All k are sending the trained metadata after training back to the central server. The central server then takes an average, and I'll come to what it does. It takes some kind of an average, right? Now you'll ask me what kind of an average it is. We'll come to that. Just park it for about 10 minutes. It'll take an average. It'll turn out that you've not achieved an accuracy, right? Because look, everything in machine learning is about high accuracy. You can't be happy with 40% accuracy, right? You can't be doing classification with 40% accuracy. It's going to be preposterous. So what this fellow will do is, we'll say, oh, you've not achieved that 0.95 accuracy. I'll send the model back to the worker nodes. I'll train them again because I have to refine my right? I have to refine the model, and I'll keep iterating k times till I achieve that accuracy. That accuracy is a function of your application, right? So there is no hard and fast rule what the accuracy is. I mean, your app may want 0.99, it may want 0.95, but remember, the higher the accuracy you want, the more the iterations, and therefore the longer the convergence time. I repeat, the higher the accuracy you want, intuitively it's obvious you'll have more and more, you'll take longer time to converge and to arrive at the final right level of satisfaction, which is a very high accuracy. So that's federated learning. So yes, it is distributed systems, but it's all about distributing machine learning models, ensuring privacy-preserving protocols. These are privacy-preserving paradigm, right? So keep that in mind, because without privacy, there is no federated learning. It doesn't make any sense, right? And so you're not sending data at any point of time. You are only sending the model. Now you may say, what do you mean by that? Well, you're sending the weights. So you're sending, and we call that metadata. So you're sending a metadata, right? Weights, for example, could be other parameters also. All right? Yeah, I will be happy to take up questions at the end of my talk. Now, the two key metrics in anything that when you work on federated learning, the two key metrics are accuracy and convergence time, right? Now, there could be other metrics. So, for example, my students are now looking at energy as a metric. That's a totally different world out there, as you all know. But energy is a metric. You really have a n-dimensional world of metrics, but we were only focusing two right now. Energy is a work in progress, and I don't have results at this point in time, but it's work in progress. So we look at accuracy and convergence time. Now, the two important questions you're always asked when you work in AI and machine learning is, what's your model and what's the data set? I hope you're working on many data sets, right? That's a question reviewers keep asking us. And I hope you're looking at many models. And the answer is, of course. You don't publish papers or write, work on your thesis with only one data set or only one model. Because if you do that, then you are kind of accused of saying, look, you can't generalize the results, right? So to convince the community, which is the research community, being industry or academia, you have to go across multiple data sets, which are diverse. I don't want similar data sets. So remember, I want diverse data sets. For example, MS is a small data set. Cypher10 is a larger data set. Remember, they're diverse. And I want very diverse models. I don't want only ResNets or AlexNets. I want probably LeNets. I want all other kinds of models, right? So remember that. You really have to compare across diverse conditions to arrive at some interesting results. All right, let's go straight into what have we observed. Where are we in terms of our understanding in federated learning? I'm not going to read all this, not required. So the simulation setup is a PySift. All of you know Python very well. PySift, of course, is a very critical simulation environment. Here are the parameters over there. I'm not going to read that. But I think an important point to note in this slide is that we have a prototype setup. Now, that is not easy because even though we have 8 Raspberry Pis, they're diverse, right? So, for example, 4 have our Pis have a storage of 8, 2 have 4, and then 4 have 2 GB. Again, remember, you want heterogeneity. You don't want homogeneity in your results because you'll be accused by very simple assumptions, right? So try to diversify, try to get more data, more models across diverse settings, which we've done. Now, you may say that 8 Raspberry Pi is not enough. Well, sure, we could work on 100, but now you're limited by the cost. Now you're limited by the many other things. Plus, it's not feasible because it takes a long time to set that environment in the lab. So I think it's a good beginning here, but we could certainly have more, the nodes in an actual POC setup. So I think the important takeaway from this slide is that don't ignore the POC, the prototype, because that does convey a lot to the community in addition to the simulation setup. Because I can simulate anything, but I cannot easily try to implement things because it's very hard to do so. You'll see in a short while from now why it's a hard problem to implement it on an actual platform. So let's look at the first set of results. So the question that we asked was, let's say you have 100 worker nodes. Are all important? Let's start with homogeneous environment. Are all the nodes important? The answer was no. We don't need all the 100 nodes to arrive at a nice accuracy. So let's look at this result carefully. So we look at the impact of the worker count. So the x-axis is the worker nodes. Don't worry about the scale. It's actually into 100. And the y-axis is the convergence time, right? We fix the accuracy. Let's say it's 0.95, which it is, right? And you look at different models, AlexNet, ResNet, LeNet. By the way, you may ask me, what's the difference in the model? Well, models are different because ResNet, for example, has, it's a very complex model. It's by definition very complicated. That's not true with so there are a different family of models, right? I'll come to other models in a short while from now. And you'll observe that on an average, and of course these all results are average of 100 runs, right? If you look at two data sets, MNIST and CIFAR 10, doesn't matter what data set you have. What's the observation takeaway from this slide? Doesn't matter what is the model that you're working with, doesn't matter what's the data set you're working with, but you kind of have a roughly convex kind of function. Look, I dare use the word convex. It's a mathematical, I think convex-like function, right? Which means that there is a number of node W star at which your convergence time is low. Before that it's very high, and beyond that it's very high. And that trend is consistent across all the models and across all the data sets. I can even add another data set and I find the same, result. Which really means that you don't need 1,000 nodes to train your machine learning model. You probably need much lower number. This result assumes a completely homogeneous environment, which means all the worker nodes are identical. I'll come to what happens when you have heterogeneity. I'll come to when you have skewed data and so on and so forth. That's a very realistic setting, but give me 5 minutes, right? So that's the takeaway number 1, right? That you have some kind of a point where you have the best results, after that is bad, and before that is bad. So you don't need to waste your time. Because remember, the more the worker nodes, you're taking more time. Remember the folk join work? We all know that the larger the number of nodes. Look, all of you know that, so one of my favorite questions is the maximum of n random variables is strictly greater than max of n minus 1 random variables, right? So that's what is happening. As you increase the number of nodes, the delays will obviously increase. So you don't want all those nodes. It's very doesn't help you. So you have some optimal number. Let's go ahead. Let's now look at, again, I'm right now beginning the talk with a homogeneous setting. I'll come to heterogeneous setting in a short while from now. Let's now look at two plots. One is the model accuracy and the other is convergence time, right? And on the x-axis, I have again the percentage of worker nodes selected, and on the y-axis are different. So here is model accuracy and here is convergence time. These are the number of nodes, 50 nodes, 100 nodes, 200 nodes, right? So these are the number of worker nodes. You find that as the fraction of worker nodes selected increase, your model accuracy increases. Not surprising at all, right? Not surprising. As you have more worker nodes, you have more accuracy. Well, because a lot more data is coming to the central server and you're taking an average or whatever. Whatever be the mathematical function, you're taking some kind of an average and you are doing a great job. But if you look at the convergence time, we find this is exactly what you saw earlier, right? At 60, roughly 60, fraction of 60%, or 0.6, right? At this number, the convergence time is probably the lowest, right? It increases beyond that and increases before that, right? So now let me repeat this point. Look at the right curve first. When the percentage of worker nodes is 60%, so you have 100, you're taking 60, right? Your convergence time is really fine because you want minimum convergence time, right? Right? But you also want a high accuracy. You have to work, it's concerted, you have to work together, right? But it turns out after 60, it doesn't matter what your numbers are because the accuracy is flat. 60 is a good number, right? So for this model, whatever the model is, for this data set, don't worry about 60. 60 is not a sacrosanct number. There is a number alpha where you will get very good accuracy because beyond that it's an overkill, it doesn't help you, right? But you have the lowest convergence time. And remember, convergence time is very critical in these applications because you're running an app. You're running an autonomous driving app and you don't want delays at all, right? And you want a very high accuracy. So you've got to take both the plots together and then arrive at some inferences, right? So this is for a homogeneous data distribution. Now what happens, let's ask another question now. What happens when you introduce heterogeneity? So that's something, well, the obvious question for us to ask. Now, just to point out, when I use the word heterogeneity now, I mean the heterogeneity in terms of the nodes, not the data. Right? I'll come to that later on. So what happens when you introduce heterogeneity in the system, in the distributed system? Not surprising. So the red is homogeneous, right? You kind of have a convergence time which is lowest around 65 or whatever. But as you introduce more and more heterogeneity, and you may ask, how did we do that? Well, it's an arithmetic progression. So the heterogeneity, right? So if it's D, 2D, 3D, ND. So the simple assumption is have an AP there. GP, of course, is another possibility. But let's start with simple assumptions. And when you have more and more heterogeneity, look at the green plot. You're finding, what is the observation? What's the inference? That your convergence, the W star is shifting towards the right. Not surprising at all. Because the moment you inject more and more heterogeneity, right, you're going to need more number of worker nodes to give you results with high accuracy and low convergence time. Again, intuitive, right? It's not surprising at all. But look, until you don't prove it, until you don't experiment with it, you really don't, you can't make any inference, right? So it may be intuitive, but it's intuitive after the results, not prior to the results, right? So that's interesting. So the more the heterogeneity you inject, your minima is shifting on the right, and so it's telling you that, well, if I have a very high heterogeneous distributed system, where maybe all the worker nodes are very different and very distinct, well, all the best, your convergence time is going to play havoc. If you want to achieve a high accuracy, right, which is, let's say, 0.95, which is standard value, whatever. So interesting, right? Let's go ahead. Now, it turned out, so one of the lessons we also learned was never work on problems, don't complicate it from day one. Let's go step by step. That's the only way we learn. Now, one of the lessons we learned was that if you go to, let me just go back, just a minute, please, if you give me a minute. Let's go back to this slide. Look, this is fine. I mean, all that jazz is okay. But what else is, look, we're looking at the intersection of networking with machine learning, right? Communication network with machine learning, which is distributed systems. What else is important here? What are the parameters that are important? So the first parameter probably is the processing power at a node. How much is the processing power of the node, right? Because if a node has a lot of processing power, then I can process the model much faster because I have, for example, 6 cores vis-a-vis 1 core, right? Number one. Number two, the bandwidth from the central server to your worker node also plays a big role. So if I have a 1 Gbps bandwidth versus 1 Mbps bandwidth, of course that's going to play a role. So the first parameter that is the networking parameter turns out to be processing power. The second turns out to be what? The bandwidth between the worker nodes and the central server. And the third is the volume of data. Volume of data at the worker node. Why is volume important? Well, the volume is very large. If you have a huge data set, my private data set I'm the worker node, will take longer time, right? But obvious, right? So there are many networking parameters that you have to consider when you're looking at the performance of federated learning models. And that's exactly what we did. We said, look, these are simple results. These are homogeneous setting, blah, 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 blah. But now let's take into account 3 parameters. V is the volume, P is the processing power, and I didn't write that because I thought I'll just talk it out. And B is the bandwidth between the worker nodes and the central server, processing power of each worker node, and V is the volume of the data at the worker node, right? And we defined the selection score S. Now, of course, you may ask, how do you arrive at that? Well, look, it's not a rocket science because anybody's guess is that a high bandwidth is good for me, right? Because I'll be able to communicate quickly. So if B is high, the selection score is low. My end goal is to have a low selection score, right? So listen to this again. I need a low selection score. So high bandwidth is good for me. High processing power is good for me. High volume, well, it's tricky. And that's why you see one by the outside. Because a high volume implies you'll have a more robust, you have great results, but you're also going to take more time. And so after intense deliberation and all meeting, it turned out that, well, this selection score, it's not a unique score. You can have your own selection score. But remember, the moment you have second order metrics, you'll have much more complexity. So it was not that complicated, right? So some selection score S, which combines all three parameters, and repeat the results, and you find again, and you plot training loss. Now the y-axis changes. It's training loss versus convergence time. And what you do is, again, you have the two different data sets. And I'll come to the right side later on. With the MNIST data set, the random, now this, right? So let's look at what this means, random bandwidth. Random is choose nodes at random. You don't care what the networking parameter. Just choose them at random. Just toss a coin or just generate some random number and choose those, whatever, alpha nodes or beta nodes, right? The random is terrible in training loss. It's the highest training loss, right? If you only look at bandwidth, that's the gray curve. So these are individual, only data volume, only computational power. But if you now combine these metrics in an interesting way, which is the brown curve, you will find that the training loss is really fairly low, right? And the convergence time is, of course, much quicker across diverse settings, irrespective of what the data set is and what the model is. Now, the model here happens to be a CNN with 4 layers, but it could be any model, right? If you look at the right side, now why did we look at an IoT security data set? Because a lot of people, when we discussed this with colleagues, they said, look, Rajeev, you have to look at real data sets. Let's look at real world apps like IoT security. Now, this came from your IoT security data set, which is available. And IoT generates huge data because you want to ensure that there's no, the data which comes out from the nodes to the edge is not, it's authentic data, it's the right data, it's secure, right? So this turned out to be a very nice data set for us. And it turned out again that, the random behaved strangely, but the good news was that the S-based again is doing very well, right? It wasn't as clear as the MNIST data set, but the S-based really was doing well. So the takeaway from this slide is, and now I'll complicate the story further, that if you combine the networking parameters in a federated learning architecture, and you look at all of them, you find that the results are better. Not surprising, again, intuitive. That turned out to be post the other results, right? All right, now if you look at the convergence time and model accuracy with 50 nodes, 100 nodes, and 200 nodes, not surprising, you will see that as the number of, so look at the x-axis. The percentage of worker nodes have failed. Now we look at the failure model, right? So the next question we asked was, what happens when nodes fail in a setting which is not perfect, which is the real setting? Node will fail, right? Why will they fail? Well, the links may fail, the node may fail because of power reasons, because of any other reason, right? It just may be a node which is out of the network for whatever reason, right? When the nodes fail, the convergence time, what happens? It's going to go down, right? But look at the accuracy, it takes a big beating, huge beating. So as nodes fail, as a fraction of worker nodes fail, your accuracy takes a big beating, right? The convergence time, of course, is lower because you have lesser number of nodes to work with. Let me repeat this. Of course, the convergence time will be lower because you have lesser number of nodes to work with, more of failing, right? But you're taking a beating on the accuracy. There's some way you have to find what that optimality is, right? So it's an interesting experiment that we performed over there. And then if you look at the
Okay, so there is a famous result by Eric Zing from Carnegie Mellon. So what we saw was that, okay, when you have a distributed system like this, right, you have something called stillness. Stillness means, writes are happening at every node, right? So which data are you getting, right? Are you getting the most recent write or sometime maybe few seconds back or so on, right? And what it showed was that, convergence time, the higher the stillness, the more the convergence time, right? So have you tried with that kind of stillness? Like there are metrics like stillness metric, gamma metric.
So the periodicity,
yeah,
right?
No, this is stillness. How still your data is.
Right. No, we've not looked at stillness in the results over here. No, we've not. But I think the periodicity is fairly. The assumption of the periodicity here is fairly normal. It's pretty practical. But when the interval is fairly large or it's very small, you have trade-offs over there. So we've not looked at that trade-off. But it's standard interval over here. Okay? Yeah, so that's the So we're not really looking at staleness, is not something that we're looking at this point in time of the weights exchange of between the worker nodes and the central server. Okay, now if you look at the overall, if you look at this plot really summarizes what I mentioned earlier, that we started with no failure model, and then we assumed failures, and we kind of injected failures, that's a better word, and not surprising at all. So as you plot the number of contributing workers versus the model accuracy, doesn't matter what the model is. I repeat, it doesn't matter what the model is, right? Because we did work around many models. You look, it's kind of clear that with no failure, your accuracy, which is red plot, is strictly higher than with failure at any point in time, for any number of contributing workers, right? So that's interesting. It tells you that the differences are significant. So when workers fail, when the number of workers or the nodes fail in the fed learning ecosystem, then remember that you take a beating in accuracy. It's important. But the interesting takeaway here is what's the delta? The delta is important, right? So if there are 40 workers, then you can see the delta here. And but beyond the point, as the contributing workers are very high, you find that it doesn't really matter, right? So when the workers are low, when the fraction is small, then the delta is very high, but beyond the point, it really doesn't matter, okay? So the failure and the no failure comparison is a very important comparison in any machine learning literature, in the federated learning literature. Okay, now here is, so what now we did was so you remember the three metrics of volume, bandwidth, right? So there was volume V, there was bandwidth B, and there's a third, right? And then it turned out that we proposed an algorithm called the federated fault mitigation algorithm. It's called FedFM. So the proposal, the algo which came out, the FedFM algorithm, I'm not going to read all that. But now let's look at, so this is a very important set of plots. Now I'm complicating the scenario now. I'll tell you what the difference is. So when 20% works, so what we do in all these four plots is we plot the FedFM, which is the black dashed line, with Fed average. All of you know what a Fed average is. Fed average exists in literature, it's well known. So what Fed average does is takes an average of all the weights that I'm getting, the metadata I'm getting, and gives you the results, right? And it keeps iterating it, but every time it takes an average, right? What we do is, the Fed FM is looking at all those parameters, right? In addition to Fed average. So it's a little bit, it's a second order in some sense, right? Going beyond the mundane. And you find, again, not surprising that the Fed FM is doing well consistently in terms of model accuracy, right? So all these plots are model accuracy. Now, irrespective of how many workers fail, 20% workers fail, or 40 fail, or 60 fail, this last plot is a prototype. So, we were always kind of asking a question, look, we want to get the similar results when we actually run this on a Raspberry Pi environment. And it turned out absolutely lovely correlation with our PySIF, right? So this last plot is a very important plot. When you run this on an actual environment, you really, we kind of makes us happy that Fed FM is doing strictly better than Fed average across at any convergence time, right? So that's interesting. So that's the first takeaway. And now we compare, let's look at the model accuracy. So if you go back, let's look at now the no failure scenario, right? Centralized means that you really, it's a dumb model, right? You're not exchanging the weights, you're sending the data. Centralized is non-federated learning environment, right? You're sending the data. So centralized is doing terribly in terms of accuracy, FedFM is doing much better, and again, very consistent across all the scenarios, right? So the takeaway again is that POC is very critical, which corroborates what we got in simulation through PySIFT. And you have to compare across very diverse environment, because just a single plot or a set of plots will not take you anywhere in terms of convincing the community that the proposed algorithm is indeed doing well. Okay, so what is so now further we complicated the work. So this was really the part 1A, if you will. What we're doing now is we are complicating the problem further by looking at non-IID data, right? Again, this is work in progress, by the way. So these are recent results. What we have done is we have now looked at the skewness of the data. Remember, I never spoke about skewness, right? I never spoke about skewness. Now you may ask me how to define skewness, but there are many definitions of skewness, right? So there is one definition, which is a standard simple definition. Zero skewness, 0.25 means that 25% nodes have a highly skewed data, and the other remaining 1 minus 0.25 are completely homogeneous, right? I repeat, the complement is completely homogeneous, but it's 25% that have skewed data, right? And 1 means that everything is highly skewed. Now look at the results carefully. You plot accuracy versus convergence time across different skewness, and what you see, when the skewness increases, you're taking a horrible beating in accuracy. But this is but skewness has, in real world application, there will be skewness. It's always non-IID, right? All of you have done basic course of probability theory. Where is the IID assumption hold? It never holds. Independent, identically distributed assumption is wonderful to prove theorems, but it doesn't hold in practice because you have correlation in data. You have spatio-temporal correlations, right? You have other kinds of dependencies. Remember the folk join model? I mean, you divide a data into two, A and 1 minus A, but they correlated. A and 1 minus A, there's A in both places, right? So when you have skewness, which is a real world scenario, you are going to take a beating in accuracy. So what's the mantra? What's the answer? Well, the answer is that you will have to run your system for a much longer time. You have to figure out mitigation. Now, what do you do? How do you ensure a high accuracy with a low convergence time? That's what we're looking at. So we are now looking at heterogeneous scenarios with skewed data, and we're answering questions that look, what is the best mitigation strategy? How do you arrive at interesting results which make both the worlds happy? Which world? Accuracy as well as convergence time. Okay? So this work is under progress. We've defined a new metric here, which the S metric has become much more complicated now, because now we've incorporated the skewness, degree of skewness. And by the way, skewness can be defined in many ways, as you know well, right? There's only not one skewness. You can have all kinds of definitions of skewness. So maybe we can repeat this with different definitions of skewness, but the fundamentals won't change. All right? So that's the part one of my talk. So the takeaway from this part is that the number of worker nodes plays an integral part in any federated learning algorithm, right? You don't need all the nodes. You probably need a fraction of the node. But what's that right fraction, number one? I'm not going to read all that, right? Number two, what happens when nodes fail? When nodes fail, you're in a realistic scenario. You have to figure out, well, what do I do now? So that's the second takeaway. So first takeaway, not all are required for an efficient federated learning model. Then when nodes fail, what happens? And finally, when you inject skewness, when you inject more and more heterogeneity, both in nodes as well as in data, how do the results compare? And so that's the key takeaway, right? Now, in terms of future extensions, which we are thinking of now, because that's the plan over the next 6 months, see, the problem with this work, this whole body of federated learning is, if the central server fails, then you're done, right? It's a single point of failure. Wherever there's a central server, if it fails, because we're complicating the problem more and more. But so now there is some work going on, and what happens when there is no central server? When each worker node is itself like a server. The problem is hard, because how will you choose the nodal? How will you choose the node which is acting as a temporary central server? Number one, how will you communicate all these weights? It's a dynamic setting, so it's a hard problem. What happens when your network architecture keeps changing? Nodes join and leave, like an autonomous driving. Let's say each car is a worker node, cars come and go in a unit area, right? In a unit time delta t. So what happens when the environment is very dynamic? Now, can we repeat the results? Well, probably we can. We've not done that. We've not done when nodes are mobile. All the results are assuming the nodes are static. Look, we can't complicate it so much that we'll have no results, right? So you have to go step by step. But I think this is an interesting next step. And of course, what happens when you incorporate fairness? Look, all of you know you are CSWE students. Fairness, again, has many metrics. There's proportional fairness, there's max-min fairness, there's so many definitions of fairness. Even simple definitions can be look at fairness and make sure, but what do we mean by fairness in federated learning? Maybe it means that the nodes that are selected, fairness in what sense? So we're looking at that in terms of like further extension of the work. And finally, can we leverage this in the homomorphic encryption setting, which, as you know well, when you send the data, you send the metadata to the server, and the server does all the computation and sends back the results, right? So can we do that? Can we leverage federated learning in the home office setting? So that's an interesting lesson. So I think very interesting problems to work on in the future. I do know that federated learning is becoming very, very important to even industries now. Because, why? Because edge computing is playing a dominant role, and you want to run fed learning on edge. Why is it becoming critical? And I'm going to wind up part one with this, is because you want to preserve privacy. Today, if there's any privacy violation, your company can shut down, right? The consequences are very, very severe. So privacy is the real reason that I want to work on federated learning and try to, but I think the question is, how do you get some interesting results, performance results, that'll keep us, give us more insights into the problem. Okay, let me quickly move on to, how much time I have, don't even know. Okay, let me move on to very quickly another very interesting problem, and I'm going to just come straight to the point, yeah. So the question that we asked was, and I'm going to part two, right? But this is again a very interesting area of work. So let's take an example. This is a complicated CNN. All of us know convolution neural networks, multi-layered networks. They have these weights, right? There's breadth and there's depth that we all know, right? Right? Depth, number of layers, breadth per layer. So this is a typical, some figure I picked up of convolutional neural network, and I'm trying to run the CNN on the edge, and I'm in deep trouble because they probably will not run because edge is very resource constrained. CNNs with large layers, right? Like your, as I come to the what CNN I'm talking about, they're going to give you terrible. They won't run on the edge. So you've got to do something smart, right? So the obvious question that we asked was, and that was, can we split the CNN? So go back to this slide. Can we split the CNN between the edge and the cloud and the server? All right. So we said, okay, let's start with a very dumb result. Let's randomly split a CNN. So I repeat, question that we're asking is, can we split the CNN, some alpha running at the edge and 1 minus alpha running at the cloud? Why? Because I cannot run a complicated CNN with a large number of layers on the edge. It won't run. I mean, it'll take a long time, and you won't, it just defeats your whole purpose, right? So let me split the CNN. So the simplest question is, well, let me randomly split it. I'll toss a coin, I will generate a random number. If it's, let's say, 19, 20 layers, maybe at layer 7 I'll split. And it turned out that's the worst strategy, horrible strategy. So then that led us to ask a question, and I think very interesting student who said, Rajeev, if you split randomly, we're getting terrible results. And I'll tell you what the results are. And he said, then how do you split that? How do you efficiently split a CNN? And then we kept asking questions. Okay, literature has answered the question with keeping only the latency in mind. So, yeah.
Have you split between multiple edge devices instead of
Great question. Great question. Work in progress. Right now, it's only one edge device. Great question. That is actually my next slide, work in progress. No. So what happens is when you have multiple edge devices, you have other nuances, right? So it's good to always start with one edge device, but even the question of splitting efficiently with one edge device is a nightmare, right? As you will see now. Yeah, but very good point. But that's also tantamount to number of cores per edge, and we have done that. So in some sense, yes, but it's not the same. All right, so now let's look at very quickly, I'm going to skip all that. So we are splitting the CNNs, and it turns out that so people have done that. Very simple experiments have been done earlier, but our objective is twofold. One is to split the CNNs so as to minimize the overall latency. Means what? Latency between what? End-to-end latency, and I'll tell you what that means. I'll go deeper into that. And also maximize the resource utilization on the edge. You really want the edge to have util max, Umax. You don't want an edge, because it's expensive resource, to be underutilized, right? So you want high utilization Umax, and you want minimum L, so Lmin. So Lmin and Umax, right? And you want to then, so the way to do is, you do a local computation of all the CNN model on the edge. You then send the intermediate results to the cloud server. You compute the remaining layers at the cloud, and you retrieve the final results again from the cloud to the edge, and wherever you want to send it, IoT or whatever, right? So let's look at the first set of results, right? Very quickly, and again, this is not surprising. So let's look at, so the x-axis is the split point, the point where you split the CNN. let's say it's 100 layer CNN, could be anywhere between 1 to 99, right? Or 1 to 100 means everything is running on the edge, right? And the y-axis is the total latency. Total latency, you don't have to read all this, not required. Total latency means latency, see what is total here? The time taken to run the CNN alpha at the edge, alpha is a split at the edge, plus the delays, the transmission delays from the edge to the cloud, because you're sending the model to the cloud, the remaining one alpha. The time taken to run at the cloud, and finally time taken from the cloud to the server, the total end-to-end latency. So it's A plus B plus C plus D. So what we did was we broke into four, the latency is broken into 4 parts. The top on the black is a total latency. You know what you observe over here? You observe that at where you split is absolutely critical, because let's say you split over here. Let's say for a given model, this is VGG16. By the way, we've taken many CNN models now. So this is AlexNet, this is VGG13, 16, 19. Let's take an example. Let's take VGG16. I'm taking any random, right? If you split at 25, vis-a-vis splitting at, let's say, 10, oh, it's a disaster in terms of latency. And we know exactly what is causing that. There is some dominant component, which is the red, which is the computational edge. So when you compute at the edge, that takes the longest time, right? Because edge is resource constrained. Other elements are really not contributing much. Other latencies are not really playing a big role. So where you split the CNN, takeaway number 1 is crucial. If you do it randomly, it's horrible. But even if you don't do it randomly, split at a higher layer, for example, your latency can be terrible. It will defeat the whole thing. So that's one takeaway from the splitting one, right? Now it turned out, this is an interesting stupidity, it turned out, and you may know this, that, well, this is nothing but a optimization problem, right? Because we are trying to, what are we trying to minimize the latency and maximize the utilization. So we arrive now at interesting, so let's first define the total delays. Total delays at the edge is this, don't worry about these constants. This is the transmission time from the edge to the cloud, the time to compute the remaining. So you compute x1 as the number of layers at the edge, x2 as the number of layers at the cloud. So x1 plus x2 is equal to L, number of layers in CNN, right? So if there are 100 layers in CNN, x1 could be 10 and this is 90, right? So x1 here, x2 there. So the delay at the edge, the propagation from edge to cloud, delay at the cloud, sum all this is total T edge. And it turned out that this is interestingly a problem, an optimization problem, which you can define as some f1, which is sum of all these delays, subject to another function, which is nothing but a function of the time that you take at the edge, right? This is a local computation at the edge. Don't worry about these parameters, the standard parameter, number of cores, processor speed, edge cores. So edge cores are taken over here, Supratik. Not the number of edges, but the edge cores have taken, we have taken that into account. But I think the problem when you have multiple edges will be a little bit complicated, because now you're talking also about how do the edges communicate. So it's an interesting problem. All right. So it's a optimization problem, and it's actually a multi-objective, because there are 2 parameters, right? There's latency and there's utilization. So it turns out to be Pareto optimal, and I'm going to skip all that. So it's really arriving at a Pareto optimal efficient solution using an epsilon constraint method, which is fairly well known in the literature. I'm going to skip to the algorithm. And now you can see that with these assumptions that we have, bandwidth is some amount, edge cores, 2 edge cores, 10 Mbps bandwidth, edge CPU speed, blah, 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 you arrive at some very interesting results, right? You plot bandwidth or memory or the number of edge cores or the number of server cores vis-a-vis the fraction of layers in the edge. The fraction of layers in the edge is an important variable, metric, and you find that as you increase the parameters, yeah. So the whole idea of disk plot, which is nothing, no rocket science here, the sensitivity. How sensitive are my results to a change in the networking parameter? Just like what we did in the federated learning work, right? But let's come to more interesting results, right? Here are the more interesting results, right? The accuracy is always a very critical parameter. This is CNN. We can't do without accuracy, right? The question is, are we compromising accuracy? No, we're not. By splitting the CNN efficiently using an optimization problem, right? I repeat, by splitting a CNN intelligently and optimally, because latency is a metric and utilization is a metric at the edge, I'm not compromising on accuracy. Look at this figure carefully. These are the number of layers. Irrespective of what model you have, your accuracy is absolutely, there's no change in accuracy. Which is critical, because if the accuracy were to take a beating when you split the CNN, then you are done. And your work is thrown in the garbage can, right? So that kind of said, oh, thank God, accuracy is not being compromised. And something that was very important in the work that we did, right? And then we repeated experiments across various models. A very important result is over here, where we compared our LMOS. So our algorithm is called latency-memory optimized splitting. Now you know what it means, right? I split based upon latency and memory, right? So this is our work, the LMOS. What do you observe from this plot? You see that if I plot latency versus the competing systems, I'll tell you what the other systems are. We are really doing very well in latency, extremely well, irrespective of what the model is. Doesn't matter whether it's AlexNet or VGG 13, 16, 19 or whatever, Delta or whatever. We're doing very well. Now, what are the other competing models? We also compared this with the worst case, degenerate case. When you run everything on an edge, right? Edge constraint only, latency only, right? This is called deep split. That's another algorithm. Random. Look at random. Look at this figure. If you split the CNN randomly, it's a disaster. Look at the latency. I mean, it's n-fold increase, right? But we really didn't know this earlier. Till we then investigated and said, yeah, you don't do things at random in anything in computer science, electrical engineering. It doesn't work. It'll give you a bound, but it won't give you a very nice result, right? Similarly, when you plot memory requirements versus the competing systems, you'll find the LMOS is doing pretty well, right? You want the memory footprint to be low, right? So you're doing pretty well vis-a-vis all the other systems. So it's kind of interesting observation. And this tells you that, And then we went ahead. We said, look, let's not stop here because the community will pounce at us. This may not be enough. Let's compare with VGG19, with no split, with MobileNet V2. These are all very well-known models in CNN. SqueezeNet. And now we take VGG19 with LMOS, that is latency memory optimized splitting. We find that our accuracy is pretty high. Latency is not the lowest, but it's not bad at all. Memory use is fantastic. It's utilized pretty well. So in some sense, we are satisfying all these parameters without compromising accuracy. And the key takeaway, therefore, is that your splitting is a superior alternative for running convolution neural networks at the edge. So if you are asked the question, should I run the whole CNN on the edge? And if the complex CNN answer is no, don't worry about splitting, but do it intelligently. Okay? Don't do anything randomly or dynamically. So the conclusion of this part is that running a CNN between an edge and the cloud is the same as solving a resource constraint optimization problem that I mentioned to you earlier at the edge that reduces latency while maximizing the resource consumption. Look, you really want high utilization, right? Otherwise you're wasting your resource. It's a pricey resource. Experiments reveal that LMOS does ensure that different CNN models may be executed at the edge, and we've compared this with even degenerate cases. So you run the entire thing on the edge, well, then there's no point, right? You could be saddled by large delays. You can run everything in the cloud, well, then you're back to your school days. Because if you take everything in the cloud, then you don't need the edge, then what are we talking about? So those are degenerate cases, extreme cases. But we have to do that because it gives you the upper and lower bound, right? So when you run the entire CNN on the cloud, or you run the entire CNN on the edge, that gives you an upper and a lower bound. It's important to get those results because otherwise you're not satisfying the community. And finally, so where are we now? So the work is not, so look, I didn't have time to add more results here, but we've also included energy in the splitting. So our other paper which came later on, which actually has some very interesting results, and I'll be happy to share with Supratik. Let's go back to the slide very quickly, and I'm going to then wind up an open question. Yeah. So if you look at this function, that only includes the utilization and the delays, right? U is so you have X, which is the total memory utilized at the edge, and then at the server, and the U edge is the output. Yeah. So the three, and you know how they came from? They came from this, right? You have three different components of delays. Let's say I had another metric called energy. Okay, energy is critical these days as far as edge is concerned. Let's say another metric here called energy, so there's plus fourth term, and we have results over there. And these are results on actual mobile phones, which the students worked on. You know, they ran on diverse mobile phone, and it turned out that, again, now go back to this slide, that our LMOS, and that, of course, now it's not LMOS, it's latency, memory, energy optimized splitting does better than other comparative algorithms. But energy is now also metric, so that work is also done now. So where are we now? We are now trying to look at, so we did run LMOS on smartphones. We are now generalizing LMOS for other network architectures and for complicated deep neural networks, right? RNNs, LSTMs, GNs, that work is not yet done. So that's work under progress, okay? So to conclude, I think, so two parts of my talk. One was, let's look at the whole federated learning performance in a realistic setting, number one. And then the other part was, because remember we talked about the marriage of machine learning and edge computing, and the other part was how do you look at the performance of deep neural networks? CNN is one kind of DNN. How do you split that between the edge and the cloud? Because edges are going to play a bigger and bigger role in time, and you've got to figure out how to do that, right? And my final comment is that today now you are seeing work on tiny machine learning. And tiny machine learning is becoming, as you know very well, Supratik, it's becoming a very important area. And I think what they will do is they try to run the entire ML on cell phones or on Raspberry Pis or even other smaller devices. And they try to figure out what the trade-offs are. Okay, so I think we are in a very interesting phase. But I hope that a lot of open problems have been exposed in the talk today. And I'll be happy now to take questions from anyone in the crowd, and now or even later on, right? So thank you for your attention, and I'll be happy to take questions.
I have three questions.
Please.
Okay, question number one is, you considered accuracy and convergence time, right?
Yeah.
You consider false positive. Shouldn't have the evaluation been done with AUC versus area under the curve versus convergence time? Right, so that's
But look, the accuracy is well defined, right?
Right.
That metric is well defined.
Right.
But then you have to start with the basic metric, right?
Okay.
And so it turns out that you start with the basic metric and get some results, and now you complicate. Your question about multiple servers now becomes an important question.
Yeah.
But look, if you don't have, multiple edges, if you don't even have result for one edge, then that becomes, because it's a very complex optimization problem.
Second question is that, have you tried, you did the CNN model, right? Because have you tried the vision transformer? Because, it will be very interesting to see how attention models work. Because, attention models have an attention on particular portion of the data, right? So when we split them, right, then the attention model gets, the attention gets lost, right?
Yeah,
So how attention models work. So that's,
We tried across multiple CNNs,
yeah.
and we were very conscious that these models should be fairly diverse,
Mhm.
because they go from REST to lead to Alex, they're very different, right?
Mhm.
Their feed forward loop, all kinds of loops and all the constraints. And so it's important to show results across diverse CNN models. But we've not, I think the work on some other totally, so non-deep neural networks, right? That's kind of,
Vision transformer.
yeah, that's work in progress.
The
Pending.
third question is that, you consider these edge devices, right? So have you considered that while the data is in a geo-replicated stroke? Geo-replicated means one portion of the data is sharded here, and the other portion of the data is residing, let's say, in Vietnam, right? Other
You mean for the edge?
Yeah, for the edges. Geo-replicated.
But this is for the federated learning work? Or
Yeah.
Federated learning work?
Yeah, geo-replicated stroke.
Interesting. So if that happens, let's take an example. If that happens, then how is it going to influence the?
Because there's a huge difference here, right? When you have
No, but see, we have multiple worker nodes, right?
Yeah.
So you were saying that each worker node has different volume as well as skewness, right?
Right.
So in some sense, you can map what you are saying to what we have done by changing the parameters. Yeah. What will change is great point. What will change is that
Because your network is not even synchronized.
that your network parameters.
Yeah.
So I think it tantamounts to work, except that we now have to have a heterogeneous bandwidth. So
Because the time is even different when you have a geometric
right,
store.
right. Good point. So the bandwidth B is considered to be constant right now, to be homogeneous, but now you have different bandwidth from the worker node to the central server,
Right.
and that's going to play a role there. Yeah, yeah. So it's a vector of bandwidth, yeah, or a vector of volumes, and sure. So the V was constant across all, the B was the same across all worker nodes, and you have the third, right? So. Yeah, any questions from anyone back? Yeah.
Have you considered modifying your definition of convergence? That is, you have a certain tolerance.
Yeah.
You can increase the tolerance. Perhaps it's a trade-off between the amount of work you have to do, which
Yeah.
is a function of if the failure rate is high, you can
Right.
perhaps adaptively change the threshold or convergence
Yes.
definition.
So good point. So the convergence is a function. So you want to converge as soon as possible. That's of course my prime objective. But you also want to converge with a high accuracy. That accuracy is coming from the application. Most of the applications demand at least 0.95 or above accuracy. You could have a 0.99 threshold there. It will take you much longer to converge there. So it doesn't matter. So the answer is yes, it doesn't matter. All the results hold. It's just that we just have a larger convergence. But all the results will hold and they will carry on in that environment. But the accuracy will come from the application running on top. Yeah. Because some apps don't require very high accuracy. Take for example many of the image processing apps, right? I mean, I'm fine with I can infer from an image which is not completely but a little bit fuzzy, and so I'm fine with that. So. But I want the convergence very quickly, and a prime example is your automotive insurance, right? There's a accident on the road, and these autonomous vehicles, or even the vehicles in the non-autonomous setting, you want very quickly to figure out what's the root cause, and you don't want to wait at all, because otherwise somebody can doctor it. So that is a prime example. So I don't want to make accuracy, or a very quick convergence. Yeah. Because they keep iterating till you achieve that metric. Any question in the back? Yeah.
So, like, when we use machine learning models, generally we test on.
Can you speak louder, please?
Okay, like generally we test on the edge machines, right? Like not training, because edge machines are not computationally intensive.
Which machine? Edge.
Edge nodes.
Right.
So the edge nodes are not computationally intensive. So generally we test on that machines, not training, right? So like even if we are trying to like take a little part of it, we are sending some some alpha amount of the work to the central node, right?
Yeah.
So in the meantime, because in the meantime the edge node would be idle, right? It won't be doing any work. So what's the point of sending only some point of work to the central node, like, because it doesn't matter like the little time.
Well, you're right. So the edge nodes will do work when they get the metadata, when they get the model, right?
Yeah.
I mean the metadata of the model. So whenever they get that, and that was Supratik's question, right? So if I get that very frequently, then I'm keeping busy. But if I get that rarely, then I'm idling, absolutely. But then the edge nodes are not only doing this, they're doing other things too. Keep in mind that the edge nodes are multiplexing many things.
Yeah.
So in real life, they're going to do many other things, and that's where your other techniques will come, like virtualization. Right? So you're keeping the edge node busy. But the focus now is that as you send your model to the edge nodes, and you have to preserve the privacy, remember. Otherwise, look, if you send the data, then you're done. Then federated learning is not the right paradigm, right? Right? So you will send the model to the edge node. I'll do training over there with my local data, and I will send back the data back to the central server, right? And your question is, well, but I have a lot of time because the edge is not. I mean, this is only a small part of the edge, right? Right? But that's okay. I mean, that's another point. I can keep the edge busy by doing many other things concurrently.
Okay, so edge is not real time. It is not time constrained like real time applications.
No. Okay, let me add to what I said. The edge will ensure that your real time, the results come out much earlier if there was no edge. Imagine doing everything. Okay, let's ask a question. If there was no edge at all, you'll send everything to the,
Central.
now, right? So ask a question when there is no edge. What are the consequences? What are the repercussions? Right? But in real life, of course, you'll have edges doing many things. And you will, right? So it's not just doing only this thing, which is my model, right? So, of course. So the time that I'm waiting, I'll do other things, right? So how you do that is another question totally, completely. So one answer is virtualization. So all your 5G paradigm like software-defined networking and virtual function, right? All these are trying to figure out how do I maximize the performance using virtualization. That's a different question over there. No other questions? Okay, so I'll be happy if you have any questions, please email me anytime. I'll be happy. Supratik and I are regularly in touch. I'll be happy to send all the papers. Some of the papers are being reviewed in transactions now, so as soon as they are done. But we have a lot of other work. So we're doing extending this. One of the challenges we've had, so one interesting work that we're doing, which is interesting, is how do you compare distributions? And we have all these Leibniz and all these measures, right? But how do you compare distributions without compromising privacy? So I repeat, you have different distributions at each node, worker node. Can we compare them? Because that is the degree of skewness, right? Something like that. So can we do that? So that's a work in progress with our students. I give that to those who are mathematically inclined, otherwise this is not the PySift or the Python. Yeah, so a lot of interesting problems here. I guess, hope I've given you an overview of what are the open topics. Thanks again for your attention.
Thank you.